In this video, we're going to look at some of the reasons why neural networks work so well as they do. Now you might wonder, why do we need to answer this question at all? And the main reason for that is that neural networks are getting pretty big. Here's a neural network published this year called GPT-3, and it comes in at a whopping 175 billion parameters. Now it's a massive engineering task to train a neural network that big, but the basic principle used to train it is nothing more than plain old gradient descent together with backpropagation. So how is it that such a simple algorithm can tell us for such a gigantic neural network how to adjust each of the parameters individually? The first piece of the puzzle doesn't answer that question directly, but it does shed some light on quite how strange this situation is. In this experiment, the authors took a simple classification task like MNIST, where labels were to be assigned to images, and they simply randomized it. So either they either they shuffled the labels around, or they replaced the images by random noise. But in each case, they made sure that there was no information about the true label in the image anymore, while still maintaining the possibility of remembering the label for the particular training instance that was seen. So they ran these experiments, and of course the validation loss was terrible. The validation accuracy plummeted to 0 because there was no meaningful information between the instance and the label. But what's interesting is what happened to the training accuracy. The training accuracy went to 100%, which meant that the network learned to memorize exactly what was in the training set. None of this solution generalized, of course, but it's still interesting that the neural network managed to do that. Why is that so strange? Well, note that during training, the only thing that the neural network has access to is the training loss. And the fact that there is a solution that allows it to reach 100% training accuracy means that in a normal training setting, the neural network also has access to those kinds of solutions. So when it has to choose between a solution that gives us 100% training accuracy and 99% training accuracy, why is it that it chooses the 99% version, which generalizes to the test set, instead of the 100% version, which doesn't generalize to the test set? And this brings us to an important point, which is that machine learning is not just about optimization. We're looking for minima in the loss surface, but when we define this loss surface in terms of our training set, we're not actually looking for the absolute minimum. So here we see a picture of that. We have poor local optima, which give us a very high loss. We have good local optima, which give us a low loss, and which we expect to generalize to the test set. But then there's also optima, which basically overfit, which give us 0 training loss by remembering the training set, but which don't generalize to the validation or the test set. So the next time you see a picture like this, or a formula like this, to explain the basic optimization task of machine learning, you should know that this is a slightly poor definition of our problem. We want to solve this optimization problem, and we use techniques from optimization to do so, but in a way we don't want to solve this problem too well. Because if we solve it too well, then we get overfitting solutions. In a classical machine learning view, you would remove those overfitting solutions by simply removing them from the model class. So the parameters theta that overfit, you simply constrain the model class to eliminate those. But that's not what we do in deep learning. Our model class in deep learning is so vast that all the overfitting solutions are well within the model class. And one picture that is often drawn to explain this is the double descent picture, which explains the difference between the classical view of machine learning and the deep learning view of machine learning. So this is the classical view, where on the horizontal axis we have the model capacity. So that's how many different functions our model can capture, depending on how we set its parameters. And on the vertical axis we have the test set loss. And if we constrain the model capacity massively, we're in the underfitting regime, where the model simply doesn't have the capacity to provide a function that fits the data very well, and we get a high test loss. And then as we increase the model capacity, the test loss decreases because the model gets better and better means to model the data. But then if we increase the model capacity too much, then the model starts memorizing parts of the data that aren't actually relevant, that don't actually generalize. And as we increase, we reach the interpolation threshold where the model is big enough to perfectly remember all of the data set. And at that point, the training loss goes to 0, but our test loss goes very, very high. Now, what deep learning has rather paradoxically shown us is that there is life beyond this interpolation threshold. If we simply keep pushing up the model capacity up and up and up, we enter into an over-parameterization regime, where our models are so over-parameterized that they can very, very easily memorize the data. And for some reason, the performance goes up again, the test loss drops again. So it's not just a conceptual picture. We actually see this if we, for instance, train models of increasing width. So here are some experiments done on the ResNet 18 model. And we see indeed this double descent curve appearing as we expect. And what's noted in these particular experiments is that it's not just the size of the neural network that gives us a bigger model space, it's also the amount of time we train. Because our training process is a walk in parameter space. So the more steps that walk is allowed to take, the more models are reachable. And therefore, the longer we train, the bigger our model space becomes. And that, too, we see in experimental results. So if we plot the number of epochs we train against the size of the model, against the performance that we see a double descent curve in both directions. So the important takeaways so far: in our optimization, the best solutions are suboptimal, local minima for the training error. And finding the global minimum for the training error is actually disastrous, because then we're perfectly overfitting. And we are saved, in some sense, by the implicit regularization of gradient descent. The fact that gradient descent, for some reason, probably to do with distance to the starting point, gradient descent prefers some parameters over other parameters. And that's what we call regularization, a preference for some parameters over other parameters. And this is what saves us here. For some reason, gradient descent luckily seems to prefer the solutions that regularize over the solutions that memorize. For some reason, gradient descent seems to prefer the solutions that generalize over the solutions that memorize. And of course, this means that initialization is very important, because the initialization is what puts us in this parameter space at a starting point where nearby solutions are the generalizing ones. That still doesn't quite explain why we can train models in such a high-dimensional parameter space. Well, one way to think about it is that high dimensionality is actually a blessing. And one way to explain that is to think about how many points there are nearby us in a parameter space of a particular dimensionality. So if we start with a one-dimensional parameter space, we think of different points that are nearby. We need to somehow define what makes a point different. So we say points that are sufficiently far apart are different. Then we can say there's probably at least 2 points that are nearby our starting point in a one-dimensional parameter space. Whereas in a two-dimensional parameter space, we can make at least 4 points that are sufficiently far apart from each other but are nearby our starting point. And in 3D, we get 8 points, and so on. So there's an exponential increase. In 4D, we would get 16 points, and so on and so on. So once we get to a 175 billion dimensional parameter space, there's a vast number of nearby points. And all of these points are therefore accessible to gradient descent. So this is what we'll call the blessing of high dimensionality. In a high dimensional parameter space, all good solutions are nearby and all good solutions are reachable by gradient descent. And there's another perspective on why deep learning works, which gives us a different route to basically the same conclusion. And to explain that, we can start with the following observation. There's a technique called network pruning, which takes a trained neural network and tries to remove as many of its connections while still maintaining the performance. These are generally the connections whose weights are near zero. And it turns out that pruning works exceptionally well. So often around 90% of weights can be safely removed without really harming the performance of the neural network that much. However, it's not true that we can simply start with a neural network that is 10% of the size and then train it, because then the performance is never quite as good. So for some reason, we need these massively over-parameterized networks in order to train them. But then once we have them, we can actually massively compress them to a much smaller network that does more or less the same thing. How do we explain that? Well, one explanation is what's called the lottery ticket hypothesis, which sort of contrasts with the traditional view of gradient descent. The traditional view is that initialization picks some random model which is largely useless, and gradient descent carefully teaches each weight what to do and teaches us where to go in parameter space so that we start doing something useful. And the power of gradient descent is that it can tell us these things. The lottery ticket view is that when we initialize a network, that particular network has a combinatorial explosion of subnetworks. And because there are so many of these, some of them by chance must perform well, whatever the task is. And what gradient descent is good at is not so much telling the neural network where to go and what to do, but selecting these subnetworks that work well and disabling others. Now, to understand this, we need to look at what these subnetworks are and how big this combinatorial explosion really is. So this is what we mean by a subnetwork. We simply start with a neural network and we disable some of its connections, and the remainder is a subnetwork. And these are just some of the neural networks you get with some of the subnetworks you get with a very, very small neural network. So to get a basic idea of how many subnetworks there are, we can say that if we have n weights in our neural network, then there are 2 to the power of n subnetworks. And some of these won't be very useful, some of these won't have complete connections from the start to the finish, but most of them will. And a substantial proportion will be quite small and still connect the input to the output. So how big is 2 to the power of n? Well, there are 2 to the power of 33 people on Earth, roughly. There is 2 to the power of 76 grains of sand in the Sahara, 2 to the power of 83 molecules in a glass of water, 2 to the power of 272 atoms in the visible universe, and 2 to the power of 400 numbers of possible games of chess. That's about the biggest number that actually means something. So that's how quickly things increase. And then if we do that for a long, long time, we get to the number of subnetworks in a model like AlexNet, which is already 8 years old. And then if we want to find the number of subnetworks in a model like GPT-3, we need to add a bunch of zeros on top of that. So just to drive home the point that this number of subnetworks is really super astronomically big. And this is why people say, well, if you have that many subnetworks, at least one of them by chance must be pretty good at performing whatever task you throw at it. And that's the lottery ticket hypothesis. The initialization of a large neural network contains subnetworks, which are the lottery tickets, which, if we isolate them, already solve the task to near state-of-the-art performance before any gradient descent is even applied, if we could isolate them. And the real power of gradient descent is not in training the model, but in eliminating the dead weight, so that these lottery tickets emerge. To show whether or not this is true, we can perform an experiment. We train a large neural network. We prune the trained neural network to a successful subnetwork, which is basically the process of killing any weights that are close to zero. Then we revert the weights that remain to the values that they had at their initialization. And with this pruned network, this much smaller network, we restart the training from these initialization weights. And what we see is that this small network is then, with these, if it has these initialization weights, is trained to the performance of a large network. While if we revert to random weights, then performance plummets. So we cannot train this small network if we initialize it with random weights, but if we isolate it as a lottery ticket with those weights it was initialized with, then we can train it to the performance of this much larger over-parameterized network. And to really do this powerfully, you can repeat the process. So here we see curves for that do that. So at every vertical bar, the network was pruned, reverted to its initialization, and retrained. And that process was repeated a number of times until we get to the point where only 2% of the original weights remain. And if we reinitialize to the lottery ticket values, we see that the performance is close to state-of-the-art, between 80 and 90% accuracy. And if we revert to random weights, we see that the performance plummets. A second experiment to really drive the point home, we can initialize a large neural networks. We can keep the weights fixed, we won't touch them. And instead we use gradient descent to find a mask that selects a subnetwork. So now we're really just looking for the lottery ticket and trying to figure out what the performance is of the lottery ticket without changing its weights. So this is a bit of a tricky thing to do, but you can use stochastic gradient descent and gradient estimation, which we'll discuss later in the course. And the result that you'll find is that the lottery ticket by itself, once we find this mask that masks out everything but the lottery ticket by itself will achieve near state-of-the-art performance. So this is really quite strong evidence for this lottery ticket hypothesis that neural networks at initialization contain these lottery tickets that really by themselves already solve the problem. Some more interesting details. If you reinitialize with random weights, but you retain the sign of the original weight, that's often enough to retain the performance of the lottery ticket. So it's not so much about the numerical values of the weights in the lottery tickets, it's very much about the signs, the plus or minus, whether they're positive or negative. And similarly, if we initialize with constant values and a random sign, so we initialize the whole network with constant values, constant valued weights, and a random sign, that also yields lottery tickets. So, what have we seen? We've seen the experiment by Zhang et al. That neural networks can memorize. They have the ability to memorize the dataset, but somehow choose not to. Probably due to the implicit regularization of gradient descent. We've discussed the double descent phenomenon, and we've discussed the lottery ticket hypothesis. And it's clear that we're getting some insight into why it's possible to train such vast neural networks, but there are also a lot of open questions, and the last word has not been spoken on these issues. In the last two videos of this lecture, we'll look at the tools you need to train deep neural networks, And in the next video, we'll start with optimizers.